Okay, specific latent heat and specific heat capacity. Okay, when do we use these equations? So this is thermal physics, and a topic you learn right at the end of year 12, or maybe your school's a little bit behind, so you'll start it in year 13. If you're doing AQA, it's going to be your paper 1. If you're doing OCRA or Edexcel, it's going to be mixed up in some one of the other papers. I just don't know that off my head. But same content. So what we're going to think about is, say I've got an ice cube at -10, right? Just pulled out of the freezer. My freezer's super cold at -10. I'm going to put it inside a beaker, and I'm going to put my Bunsen burner here, heating up. Okay, so I do have some flame here all the time heating up. Okay, the first thing that's going to happen is my ice at -10 is going to heat up, heat up, heat up, to eventually it reaches 0 degrees Celsius. So again, what happens first is my ice at -10 heats up, temperature increases, 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 till it hits 0 degrees Celsius. Okay, so the whole time that the temperature was increasing, because this stands for a change in temperature. Remember in physics, that Greek letter delta stands for just a fast way of always writing change, because we're lazy in physics. So because there's a change in temperature, we always use this equation here. To calculate how much energy went into the ice cube, we need to know the mass of our ice cube. We use the specific heat capacity of the ice cube times that change in temperature of the ice cube, from 0 to 10, which is 10. Then once we hit 0 degrees Celsius, that's when we know that's a change in state. So what happens then, the heat keeps going in, it keeps going in, but what's happened is used to break those intermolecular forces. And my ice cube at 0 degrees Celsius will change into water at 0 degrees Celsius. So the temperature will stay the same while it's changing state. So even though we're still putting heat in, that heat isn't used to increase the temperature, it's used to change the state. So the flat lines represent a change in state, and that's when we use this equation. That the energy we input there is whatever the mass was of our ice cube times that specific latent heat of fusion to change state from that solid to that liquid. So now what we have is our liquid at 0 degrees Celsius. I'm still heating up. I've never turned off the power. Still heating up, heating up, heating up. My liquid is going to keep increasing temperature, increasing temperature, increasing temperature, like heating up my water in a kettle. So my liquid keeps increasing, increasing in temperature until, again, we reach this 100 mark. Okay, so it's going to increase in temperature till I reach that 100 mark. My water is at 100 degrees Celsius. For this part of the graph, because the temperatures are increasing, the kinetic energy is increasing, we can use this equation again because there's a change in temperature. So I'll use whatever the mass I had times the specific heat capacity of water, right? Because it's water now, times that change in temperature, which from 0 to 100. Once I hit 100, even though I'm still heating up, that heat is now used to change state from that water into that gas. So this is my gas moving out of the beaker. So then we know there's going to be a change of state at that 100 because all of the energy now put in is used to break up the rest of the intermolecular forces and change that liquid water into a gas. And we can calculate that energy again because we can do the energy there is whatever mass